Imagine driving a car down the highway at 80 miles an hour, and instead of draining the gas, the engine actually fills the tank up. The further you drive, the more fuel you create. In the realm of physics, this paradoxical concept actually exists. It is called a fast breeder nuclear reactor. This diagram shows the core atomic mechanism at play. When a single, fast-moving neutron strikes an inert sphere of depleted uranium-238, it triggers a transformation. The atom absorbs the stray neutron and decays into a highly reactive, fissile isotope, plutonium-239. By burning fuel to trigger this reaction, the reactor produces more fissile plutonium than it consumes. It effectively turns inert, discarded nuclear waste into thousands of years of power. To make this transmutation work, as we see in this animation, the free neutrons must maintain their extreme kinetic energy. They must travel roughly 10,000 kilometers per second to convert the uranium. But standard commercial plants use water to cool the core. High-velocity neutrons plunging into water collide with hydrogen atoms, immediately losing momentum, killing the breeding process. To build a machine that breeds its own fuel, engineers had to remove water. They had to invent a new way to pull intense heat away from a nuclear core, pushing their designs into highly dangerous industrial territory. Their solution was a liquid metal coolant, specifically molten sodium. It flows smoothly, transfers heat highly efficiently, and most importantly, it allows neutrons to pass through without acting as a physical brake. The chemistry of sodium, however, comes with a severe penalty. If it is exposed to the oxygen in ordinary air, it spontaneously ignites. Worse, reactors rely on the heat from the core to boil water and spin electrical turbines. If liquid sodium comes into contact with that water, it triggers a violent explosive reaction. This places the reactor inside a terrifying mechanical trap. A single microscopic fracture in thousands of feet of high-pressure piping or a solitary faulty weld guarantees an immediate chemical fire. During the 1970s and 80s, governments operated under the assumption that global uranium reserves were rapidly running out. In response, they spent billions rushing to construct sodium-cooled breeders. France constructed the massive Superphénix plant, but constant sodium leaks plagued the facility. Out of its 12-year lifespan, the reactor was shut down for repairs more than half the time before being permanently closed. Japan attempted to scale the technology with their Manju prototype. In 1995, intense vibrations caused a temperature sensor to break, spilling molten sodium and sparking a massive fire that kept the reactor offline for decades. Repairing these failures is agonizingly slow. Because oxygen and water are strictly forbidden, technicians cannot simply walk in to fix a pipe. They must entirely drain the radioactive coolant and flush the system with inert gas, turning a simple mechanical fix into a multi-year project. The financial drain of these enormous maintenance delays, combined with the extreme safety protocols required to prevent explosions, forced the Western world to abandon the fast breeder. There is also a secondary consequence to this physics. The exact same plutonium-239 harvested to fuel the reactor is the ideal fissile material for nuclear weapons. This flowchart maps a closed fuel cycle. To keep the reactor running, the newly bred plutonium must be chemically separated from the highly radioactive waste. Once it is isolated, that pure plutonium can easily be diverted toward military applications. Operating a fast breeder creates a steady supply of weapons-grade material by default. Deploying this technology anywhere forces neighboring countries to calculate whether they're looking at a civilian power plant or an active bomb factory. Despite the global retreat, India recently crossed a major threshold. In April 2026, their new 500-megawatt prototype fast breeder reactor at Kalpakkam attained first criticality. India possesses very little natural uranium, but as highlighted here, the subcontinent harbors enormous underground reserves of thorium. To utilize it, India must first operate a plutonium fast breeder. Stray fast neutrons bombard the thorium, converting it into uranium-233, fueling their next generation of reactors. The catastrophic chemical risks of liquid sodium are entirely known to the engineers at Kalpakkam. For them, mastering this hazardous process is a necessary gamble to guarantee total energy independence for a population of over 1 billion people. The lingering question is whether modern materials, predictive AI monitoring, and advanced robotics can finally tame the extreme volatility of liquid sodium. If a nation can operate a breeder reactor safely and economically, they secure a blueprint for 1,000 years of zero-carbon electricity, running on a closed loop of recycled waste. The fast breeder reactor remains a technological duality. It offers a self-sustaining cycle of power, yet it functions only by remaining perfectly balanced on the razor's edge of catastrophic chemistry and nuclear proliferation.